Okay. Okay. Yep. Here we go. So, Kevin, what kind of question do you have?
I just kind of wanted to go back to the master theorem and maybe see another example
Okay. Yep.
of how to solve.
Yep. Give me 1 second. Let me find the master theorem. Okay. So let me share my screen here. Okay, let me share this one. Yes, Kevin, can you see my screen?
Yes.
Okay, good. So for the master theorem, we are trying to solve a problem like this. So Tn, so this is the cost of running a particular algorithm. And then we are trying to reduce this problem that has the size of n into a smaller problems. And each of the smaller problem, we have the size of n divided by b. So we are reducing one problem into several smaller problems, and then there will be some additional costs. Say, okay, say, well, for example, we want to have a, say, mean of an array. So this array has n items, right? So, and then we are trying to look for the mean. So this is the mean, and then we have an array, right? And then we want to figure out the mean. And say, for example, for this problem, what we can do is we can divide that into, for example, 3 smaller questions. Oops, say, and let's say hypothetically, for each of the subproblem, we have n divided by 2, and n divided by 2, and n divided by 2. Okay, so we are dividing one problem that has the size n into 3 smaller problems, and each problem has the size of n divided by 2. So if we want to grab this one, and what you can see is, let me copy this one here. So in this case, what is the A value? A means how many smaller problem we are trying to divide this problem into. So in this case, it should be a 3, right?
Yes.
Okay, so we are dividing one big problem into 3 smaller problems. And then what's the size of each of the smaller problem? So what is the B value?
2.
Yes, it is a 2, because for each of a smaller problem, and the size of the problem is n divided by 2. And then, well, there's also a cost that after, well, for when we create this divide and conquer, every time that we do this divide and conquer, there could be some additional cost. And for example, this Fn is, say, 1.5 n. Okay, so let me rewrite this. So now you have a Tn equals 3t n divided by 2, and then plus 1.5 n, right?
Yes.
Okay, so this is your recursive version of Tn, right?
Yes.
Okay, so we are at this place. So A equals 3, B equals 2, and then Fn is 1.5 n, right?
Yes.
Okay, so those are the information we know. And then we want to figure out a value. So that is log base b and then a. So this b is going to be a base number. So let me see if I can make it smaller. So it should be like this, right?
Yes.
So log b is going to be a 2. And then what is the a? A is going to be a 3, right? So for this log, well, if you remember the log, a log curve should be like this. So here we have the 1. So because this 3 is higher than 2, so we are going to have somewhere here. So this value, if we want to know this value, it should be 1 point something. So I'm guessing it is 1.3. Okay, so this is my guess, but this is guaranteed this value is going to be higher than 1. Okay.
Okay.
Yep. And then what's the next step? The next step is we want to do a comparison. So we want to figure out, so n powers log BA versus Fn, which one is faster or which one is higher. So in this case, n powers, for example, 1.3 is going to be faster than 1.5n. So because this 1.5 is a constant, and this one is n powers some value greater than 1, but this is n powers 1. So this one is going to be higher. So do you have a question on this part?
Sorry, I'm trying to.
Okay, so
Can you say that again?
Yes. So, well, if we try to see the growth of n, so if you have a n, so this is going to be a linear growth. Is this correct?
Yes.
Okay. And then how about n squared? N squared is going to be a quadratic curve,
yep,
like this, right? So this one is going to be n squared, right? So what we know is n squared is going to be faster than n, right?
Yes.
Yep. And then what is n powers 1.3? So n powers 1.3 should be somewhere in the middle, right?
Mm-hmm. Yes.
So n powers 1.3 is going to be faster than n.
Mm-hmm.
So this means n powers 1.3 is going to be faster than 1.5n because this 1.5 should be considered as a constant value.
Okay.
So this is what we know. N powers log BA. So I want to make it smaller. Is faster than Fn. This is what we know, right?
Yes.
So n powers log BA is faster than Fn. So which case it is? So this will give me case question mark. So let's go back and look. So n powers log BA goes faster than Fn. So this will give me the case 1. So what is case 1? Case 1 is theta n log BA. So this means for this algorithm, this will be case 1. And to solve this recursion, it's going to be n powers log 2, 3. And then this 2 is going to be a base number. Okay, so this is how we solve this recursion.
Awesome.
Okay, so well, to solve a recursion, so the general process is you want to, well, sometimes I may give you this kind of TN, or in some of the algorithms you may have to study this algorithm, and then you have to figure out this TN by yourself. And after you have this TN, well, you answer this part: what is the A value, what is the B value, and what is the Fn, and what is the value of the log BA. So for the log BA versus, so let me change another color. So log BA is here, right? So this is a log BA. And versus Fn. You want to do a comparison and figure out which one is a higher one. So, and then depending on log BA, n powers log BA versus Fn, which one is faster? There are three possibilities. So number one is, well, this guy, n powers log BA is faster. And number two, well, they are equally fast. And number three, well, Fn is faster. And then it will put you into three cases of the master theorem.
Okay.
Mm-hmm. So any other question?
No, that makes it a lot simpler.
Okay, good.
I've just had problems really figuring out the master theorem. So.
Okay, well, but the master theorem won't be the focus of the midterm 2. I can't promise you that it won't be in the midterm 2, but in midterm 2, we mainly focus on the content between after the midterm 1 and before the midterm 2. So that content will be the focus. Okay.
Okay. Yeah, I think I got all the algorithms down. It's just that I still had trouble with the master theorem. So
oh, okay, yeah.
I want to make sure I understand it, especially
yes.
like moving towards the final.
Yeah, in final, you're going to see master theorem again. I guarantee you.
Awesome. Cool.
Okay, and in Matthew, I want to remind you that this we are recording this problem session because one student says she really wants to come, but she cannot. So, she requests me to record this. So, are you okay with that, Matthew?
Yes, no,
yes.
That's fine.
Oh, man, I didn't see him.
Okay, yeah, and Matthew, I remember you want to ask about the coding homework 5, right?
Yes.
Okay.
So I've been looking in the book and, trying to recognize where I found where the universal and also the multiplication, like hashing portion was in the book.
Yes.
And I see there's, some explanations in the book that just don't make sense to me. But, I also know there's little things when it comes to hashing where a function can just be a math formula or something like that. And after looking over it a little bit more this morning, I almost wonder if I'm just putting in two formulas that make up those two functions.
Yes, for the hashing one, you definitely want to create two additional hash functions in your hash table. So eventually, the goal is you have 3 hash functions that you can choose from.
Okay.
So give me 1 second. Let me open up my Python workspace.
Okay. I take it when you mean the 3 hashing functions, I saw that. I take it it's the one that you put in there, which is the traditional hashing.
Yes, right. And then 2 additional hashing functions.
Which is universal and multiplication, correct?
Yes, right.
Okay.
So give me 1 second. I'm trying to bring up the right project. Oh gosh. Wait.
I figured it was better.
I haven't used this PC for some time.
Okay.
So everything looks strange to me.
Gotcha. Yeah, it made more sense to try to figure out what I'm doing here instead of going down 100 rabbit holes over the weekend. So.
Oh, yes.
Yeah.
That's the reason that I'm trying to hold this problem session so you can ask me questions. Okay, yes. Okay, so let me. Okay, so let me share the screen again. Okay, and then, Kevin, is this okay if I erase everything here?
Oh, yeah, thank you.
Okay, good. So, what you need to do is, Matthew, so on this hash table, say, let me draw a big box. So this is our hash table, hash table class. So hash table class. And then inside, we want to have 3 different hash functions. So, well, we have already built in one, that is the division. And then we also want to have one multiplication. And then we also want to have a universal. Okay, so those are the 3 hash functions that we can prepare. So, and then, well, what in the hash table lecture. So, well, the philosophy that we want to have a group of the different hash functions, and then when we initialize a hash table, we randomly pick one. So the philosophy is, if we use one of the hash function consistently, there will be some of the bad case that if we have a bad data set, so this set of the data come to my hash function one by one, and eventually it can kill my hash because, well, for each of the hash function, there will be a killer data set. So what we are going to do in this small experiment is we want to create a collection of hash functions. So here, this is what we have here. This is my collection of hash functions.
And we're going to randomly pick from those, correct?
Yes.
Okay.
Yes. And then, and for example, when in a process of creating a hash, so what I in this working process, and what I will do is, for example, I want to say create a hash, and then later I may try to put some data. So, and after I create a hash, and then I may say add some data. And then later, I may also try to remove some data. So, and then I may also try to use the key to get some data. So those are all the things we can do with a hash function, right?
Yes, yes.
Okay, so let's talk about that. Well, when we create a hash function, and then we have to randomly pick a hash function, and then we are going to use this hash function consistently, right?
Mm-hmm.
Okay, so well, being consistent is a key here. So for example, when we create this hash, and then I do a random number from 0 to 2. Okay, so for example, I use this random number 0 to 2. And then based on this random number, and then if it is random number 0, I'm going to use the division method. If it is number 1, I'm using the multiplication method. Right. And if it's number 3, I use universal hashing. So let's hypothetically say I randomly pick a 1. So this means in this hash table, I'm going to keep on using the multiplication, right?
Yes.
So, and then when we are trying to add a data, so I'm trying to add, for example, say the key is a 32, and then the value is a string called panda. Okay, and then when we have this key 32, what do? We want to send this 32 to this multiplication function, right? So what you need to do here is, for an incoming key, you want to apply the multiplication hash function.
So I kind of, want to question you here. In the item, or in the what you already have prepared, which looks really similar to the one that I did in data structures. You have hash function, parameters, self key size, and it's just key mod size. And then you have a rehash. I actually had a resize one in mine as well. but and then the rehash is just a whole old hash plus one mod size.
Mhm.
When I look into, say the multiplication, it's, within a bracket, M parentheses K times A mod one. And I'm wondering if that's as simple as that. And maybe I don't want to say too much to where I'm giving away an answer or anything like that. But, I'm wondering if it's that easy.
I think you are close. So, there are two separate tests. So number one is you define the hash function. So for the hash function, you tells when you have a key 32 incoming, you want to map the key 32 to a correct slot inside of your hash function, inside of a hash table. This is what your hash function does.
Mhm.
And then you don't need to worry about the rehashing, because rehashing will be done by a linear probing anyhow. So it doesn't matter we are doing the division or multiplication or universal hashing. When we have a collision, we will always do the linear probing, and linear probing has already been implemented in the rehash method. So you don't have to worry about that. So for multiplication and universal hashing, you only need to worry about one thing. That is, when you have a key coming, for example, 32, which slot is the number one slot you want to try to put it into. Okay. And apply this hash, and then, for example, 32, and then say should go to slot 5. And then, this is what you want to do. So you want to add the 32 to slot 5. And if you cannot put the index 32 into the slot 5, and then in the put method, there is a rehashing call already. So you don't have to change the rehashing part. You just need to make sure that the multiplication is implemented correctly. Okay.
If I'm understanding you correctly, I don't think this is going to be as bad as I thought it. It makes sense.
Yeah, so you are worrying about the rehashing part, and the answer is for the rehashing part, we are doing a linear probing, and it is already done.
I wasn't so worried about the rehashing part as I was just making sure I understood what I was putting for the multiplication and for the universal. It's not some long complex.
No, it should. Right. In my solution for multiplication and universal, they are just like no more than 3 lines of code.
3 lines. Okay. All right. That makes sense.
Okay, but Matt, let me remind you one thing. So in the put, okay, so give me 1 second. Let me stop sharing this one. And then I want to share my pie chart. So can you see my pie chart?
Yes.
Okay.
I can. Sorry, I muted myself again.
Okay, no worries. So, and let me remind you about the consistency. So, say if you have an incoming key you want to put into a hash, and this is, for example, 32, right? So, and then what is your hash value? So in the implementation that we started from, there's only one hash function. And this hash function is the one by default. And then we send this key 32. And then this hash function will tell me, based on the hash function, which slot does the key 32 belong to. But when we did our updated version of the hash table, we have 3 hash functions. When we pick one, we want to use that one consistently. So this is something you want to pay attention to, because by default, it will use just the hash function, but we have a total of 3. Okay. So for example, if you have a random value here,
that hash or that hash value is going to have to change.
Yes,
to
right.
a random.
So
Okay.
if you at the very beginning, when you construct this hash, when you construct this hash table, and then you randomly pick a value which is 1, because you want to get a random number between 0 and 2, right? So let's say if you randomly pick a value 1, and this means in the rest of the life of this hash table, you want to use multiplication all the time. So you have to figure out a way to code that into your hash table, so to make it consistent. You know what I'm saying?
Yeah, no, I absolutely know what you're saying. So
Okay.
I can run the program once, right? And
Mhm.
it'll pick a random method, whether it's division, multiplication, or universal. But then once it picks that for this run, and it has to stick with that method. And then if I run the program all over again, it could potentially choose a different method. Is that correct?
Yes, yes, this is what I mean. Great.
Sure. No. And I'm trying to think, you know, I'm looking at it too, but without reading back through it all, was there something else in part 5, hashing.py, that we need to do other
Well,
than-
you have to fix well, at the beginning of the put and at the beginning of the get, you have to fix it a little bit, so that when you are adding a new value, or when you are retrieving a value using a key, you are applying the consistently the right hash function we picked when we first construct this hash table. So there's a little bit you need to change in the get and in the put.
Okay, I definitely see what I have to change in the put, and maybe I just have to use my own mind a little bit to figure out what
Yeah,
I
so
need.
if you see the put part, in the get part, you want to change the same thing.
Oh, okay. Yeah, actually, now that I've minimized the zoom a little bit, now I can see both. Yeah, I see where that would be the exact kind of the same. So I have to change the get to match the put. Okay, I got
That's
you.
right. So, well, the argument is simple. So when you create a hash table using a specific hash function, and then in the rest of the life of this hash table, you just use the same hash function consistently, and that's it.
I think I got a handle on that one. I haven't taken too much as much of a look on number 6, but the understanding of it made more general sense. So hopefully I can get that one on my own and get off to this appointment.
Okay, so
you-
well, I can talk to you a little bit about the question 6. So what we are doing is we want to do a min heap of, in this case, I believe we are doing a min heap of 5 values, only 5 values. So let me show, Matthew, is this okay if I erase everything here?
Yes, you're fine.
Okay, good.
Yeah.
So here, so I want to create a min heap of up to 5 values. So min heap up to 5 values. So maybe we have 5 values or even less. Okay, and then here is our test case. Oh gosh. So can I do a paste? It's not so readable. Too bad. So give me 1 second. Let me try to. I want to get rid of this. Okay.
I do the same thing. I use paint for a lot of little things.
Yeah. I just want to have a decent screenshot. Okay. Good. Here we go. Okay. So well, this is a min heap. but we are using the min heap to grab the 5 highest values in this sequence. So if we want to knock down this one by one, so the first value is 5, right? So we put this 5 inside, and then because this min heap can accommodate up to 5 values. So if we have less than 5 values, and then we can put them in. So 6, okay, the heap is not full yet, so I'm putting 6, and then 3, okay, I'm putting this 3. And then for this 4, I'm putting this 4, and then for this 7, I put 7. So now my min heap is already full, right?
Right.
Okay, and then if I have an 8 incoming, and the philosophy will be every time we have a full heap already, we want to kill the one that is the smallest, and then I add the new one. So in this case, 3 is the smallest. So I want to kill this 3, I want to add the 8. So all those values should be fixed in the min heap to make it still a valid min heap. But after we have this 8, those are the values will stay in my min heap, because my min heap only keep record of the top 5 values, right?
All right.
So in the next one, we have the 18. So when we want to put the 18 in, we want to kill the smallest value again. So the smallest value will be 4, and then I'm putting in this 18. So anyhow, every time when I have a new value coming in into a min heap, I want to kill the smallest one, and then I want to add the new incoming one, and then I have to fix the min heap again to make it a min heap. So 28. So I'm going to kill the lowest one, which is 5, and then I add 28. So how about 2? So do I even want to put this 2 in?
No, you want to.
No, because this 2 is the smallest value is 6, right? This 6
Right.
is higher than 2. So this 2 won't even be in my top 5. So this 2 won't be in. So this 2, no, I'm not considering it. And then for 38, I'm going to kill the smallest value, which is 6. And then I'm putting the 38. So in this process, well, when we have a new value coming in into our min heap, we want to kill the smallest value, put the new value in, and then we want to make this min heap still a valid min heap. So the implementation of the min heap is already provided. So what we want to do is we want to implement this data structure. So we always keep a record of the top 5 values.
Okay, that makes a lot of sense. Just because I have to get to my appointment soon, I do have one, non-fundamental question about how many lines would you say your solution is for this? Just so I'm not going down
well, for my class of the n highest type, let me give you an idea very quick. So I have no more than 20 lines of code in
20
the
lines.
nth highest type.
That's to what you add it to it, right?
Well, let me stop sharing here. Oops.
Yeah, I don't want to give anything away. I
Right.
noticed
No,
that
I'm definitely not going to share
Yeah.
share my solution with you guys, but I can give you some idea. So here on this hashing dot wait, so ins this one. So here we have a min heap implementation, right?
Yep.
So for this min heap, you don't have to change anything.
Okay.
And then in your class of the nth highest type, what you want to do is you want to create well, I think I created 3 methods here. So in the constructor, so well that will be the def and underscore init, right? So and then in the init, you want to say the size. So the size will be here, and then in the constructor, what you want to do is you want to do a self dot heap equals, and then you want to construct a min heap here. So you want to do something like this. So inside of your constructor, you want to build a min heap inside of your nth highest type object.
Okay.
But you only want to touch this class, and then for this code, the code in the min heap, you don't have to touch it at all.
Okay. I think that helps me get started. I definitely appreciate all the help and everything. So.
Okay, cool. So, well, I know you are about to go to your appointment very soon. So do you have any other question before you go?
I think number 5 got me helped started a lot, and I think you definitely put me in the right direction for number 6. So thank you so much.
Okay, cool. So, well, I think feel free to leave, and then I will still stay in this Zoom for next 20 minutes. Okay.
All right. Talk soon. Have a good day.
Okay.
Bye.
Bye-bye.
All right, Dr. Song, can we
Yes.
can I schedule an appointment to talk to you about the grad project maybe sometime next week?
Okay. Give me one moment. Let me bring up my calendar very quick. So I'm going to pause